welcome back. So, this is lecture number 9 and today we are going to talk about variable frequency modulation technique. So, in this lecture I am going to talk about variable frequency control and which include constant on time modulation, constant off time modulation, hysteresis control and some aspect of steady state analysis. So, variable frequency control method, when you say variable frequency, because in the previous lecture we found that on time, off time and total time. In pulse width modulation we kept total time constant and we varied on time or off time, like we saw in the previous lecture, like whether it is trailing edge or leading edge modulation. And in analogous sense, in variable frequency also, sometimes we control on time by keeping off time constant, sometimes we control off time by keeping on time constant, sometimes we control both on and off time. So, these are the like a different technique that we are going to discuss now. So, if you recall fixed frequency peak current mode control, where we have considered this is my control current, that means my peak current reference. Okay. So, this is my peak current reference, and this reference inductor current will be compared with this reference. Okay. So, inductor current will be compared with this reference and the output of the comparator is used to reset the, we have already discussed this in the fixed frequency control technique. Now, if we look at the waveform, the top waveform, this corresponds to peak current mode control and this is using fixed frequency trailing edge modulation, where this in this fixed frequency modulation, this is our external fixed frequency clock, that is a rising edge. Whenever the rising edge comes, the switch turns on, like this pulse, I am talking about this pulse. The switch turns on and whenever inductor current reaches the peak current, here it is the control current, then the switch turns off and the switch continue to remain turn off, like remains off until the next clock is come, like here again it turn on. And we also discuss about the reset dominated, set dominated, like whether reset dominant or set dominant, that we have discussed. Now, what I am trying to say, in this case we have control peak current. Here also we can control the peak current. We can keep the same analogy, that means we are controlling the peak current. But in this case we are keeping this off time constant. Okay. So, in this case we are considering the off time to be constant. So, this is my off time that is shown here, and on time is coming from where? That is coming from the comparator when the inductor current reaches the peak current. So, T off is constant, unlike in trailing edge modulation where the time period was constant, here time period will not remain constant. Now, how to generate the trigger pulse? So, earlier it was a switching pulse which was a fixed frequency clock, but here this trigger pulse is not a fixed frequency pulse. How it is coming? Who generates this trigger pulse? So, we want to first consider constant on time modulation. What does it mean? If we take the output voltage of, it can be a buck or a boost converter or any DC-DC converter, if we compare this output voltage with the reference voltage, and this is the comparator, and what does the polarity shows? This is a comparator and output of the comparator is a QC. It shows the output of the comparator will go high when output voltage will be below reference voltage or reference voltage is above the output voltage. That means when the positive terminal is higher than the negative terminal, then comparator output goes high. And here we are detecting the positive edge of the comparator output, that is the pause edge. Then what we are doing, this positive edge is now it is going to trigger this monoshot timer, that means monostable multi-vibrator. It is normally off whenever it accepts or whenever it receive a positive edge trigger signal, then it start counting because it has a preset on time value or timer. So, it will remain active as long as the timer finishes counting. That means, whenever it accepts a trigger pulse, it goes high at high state, which is an unstable state, and remain at high state until the timing value like counting is complete. When the counting is over, then it actually goes to the low state, and then that way we can generate the gate signal directly. So, this is the waveform. You can see the output voltage when it is above the reference voltage, the comparator output was low. Whenever the output voltage goes below reference voltage, then comparator output QC will be high. When this point the QC will change state, it will changes from 0 to 1 state, it changes from 0 to 1 state, and when it changes, then the positive edge is detected by this trigger pulse edge detection circuit. So, this is my edge detection circuit, this detect my positive edge, not the negative edge. So, it is particularly pos edge or the positive edge. So, then it activate the monoshot timer, and the monoshot timer remain active till this counting value, which is the counter value which is set, and during that time this output will be high, and this is the on, that means the on state of the DC-DC converter. Then once the timing value is computation is over, the timer actually finishes its counting, then the Q goes low, and it will remain low until this output voltage again reaches the VREF value. That means, as long as the on time, the switch is on, the output voltage rises and it goes above the reference voltage, and whenever switch off, that means the voltage will start falling, and then when it comes below reference voltage, then actually again the trigger pulse detects a positive edge and it activates the monoshot timer. Please remember, the waveform here showing is the capacitor voltage. That means, even if we turn on the switch, it will not immediately charge the capacitor, because we have discussed in the previous example, like in previous lectures, that inductor current, if you take the inductor current, a capacitor current waveform, the capacitor current actually starts from negative value. As long as it crosses 0 value, the voltage cannot rise. So, when the capacitor current become positive, then voltage start rising. So, that is why, so this is it is basically the output capacitor voltage. Now, this looks like a very simple technique. We are just talking about V0 and VREF and just a edge detection circuit, comparator and monoshot timer. And this technique is a very powerful technique, but in this form we may not be able to use it, particularly during transient, and that we are going to discuss. So, what is the problem with the constant on time modulation? Now, we are assuming that when the switch turns off, that means I am talking about this particular phase when the voltage is V dash, we are assuming the output voltage should be above the reference voltage, and this is typically happen for steady state condition if you have sufficiently higher on time. But now, my question is, what will happen if the output voltage after the on time is over, that means your monoshot timer goes low, if the V dash is lower than VREF, That means what happens if the output voltage is smaller than reference voltage after switch turns off. That means I am talking about this particular instant. What will happen? So, the comparator output QC is low, in this case it is low, there is no edges also, monoshot timer also is not activated. So, the timer remain continue, that means V dash is less than Vref at t equal to t dash. So, this is a time t equal to t dash, and QC continue to remain high, sorry, it should be low because V0 is okay, QC is continue to remain high, I am sorry, it should be high, yeah, because here output voltage is lower than the reference voltage, and if this is lower than the reference voltage, then output is high. But since there is no edges, that is it is remain high, it remains high, there is no edges, there is edge detection circuit could not identify an edge. So, the timer remains, the switch remains off. So, there is no edge detected. So, Q remains off, this switch remains off, and V0 further decreases. So, and what will happen? The output voltage completely collapse, because output voltage will continue to decrease and this will remain high and high, and output switch remains off. So, the whole system will collapse, and this happens in the during the transient. So, how to avoid such scenario? How to solve? That means because in commercial constant on time controller, you need to put, so this is a straightforward that we discuss. It is in the very basic form. Now, the turn on problem, that means we need to turn on the switch if we find that the output voltage is lower than the reference voltage, otherwise the voltage cannot rise. So, how to solve this problem? The solution, we need to introduce a minimum off time. That means when the switch goes low, that means after the on time, the monoshot timer completes its counting value, the switch it will go off, and we need to identify at the falling edge of the Q that whether the comparator output, that means this output is still high or not. If it is still high, then we will wait for some time when the switch will be off, that is called minimum off time, and then we again turn on the, we will again create a edge trigger signal to turn on the monoshot timer, that means to activate the monoshot timer. So, by that way we need to introduce. How can I do that? So, now earlier we use this trigger pulse directly as the input to the monoshot timer, but now it is not connected directly to the monoshot timer. So, it is, there is additional circuit which is a minimum off time detection circuit. How does it work? So, it takes the input of the gate signal Q, and it takes the output of the comparator, and it also takes the edge detection circuit output, that means which is placed after the this comparator output. Then what it does? So, first it is checked. Whenever the monoshot, that means when the switch turns off, that means when the monoshot timer completes its counting, that means on time is elapsed, it detects the negative edge, and that means it creates an edge which is a falling edge, and that is delayed by a time delay tau d. So, you can use a delay circuit, that means you can use a shift resistor to delay the timing, how much delay you want, and this will lead to a dash, f falling edge dash, that means another signal. And now that means we created a pulse after detecting the falling edge of the main switch, and that we have delayed, and that signal is ANDed with the output of this comparator. That means if we find the comparator output still remain high, because we have a problem. What was the problem? Even after turning off the switch, if we find the comparator output remains high, no edge is detected, then we have a problem, the main switch was off. So, first we check whether the comparator output is still remains high after the delayed the trigger pulse. That means during this time we want the monoshot timer should remain off or the switch will remain off. If this signal still remains high, then output of this AND gate actually pass this trigger pulse, that means the delayed falling edge trigger pulse, and that is ANDed with this trigger pulse, that means the trigger pulse which was coming from here. So, ANDed means at that delayed interval it may not find any positive edge of the comparator output, but it will find a falling edge signal. That means, sorry, this is a rising edge signal which was originally considered here. This is a rising edge signal. It is ANDed with this falling edge detection, which is detected and it is delayed by a minimum of time, and OR operation of this falling edge, delayed falling edge signal with the rising edge signal will be my trigger pulse for the monoshot timer, for this monoshot timer. So, this monoshot timer is now used. Now, we can solve this problem. In fact, in subsequent lecture I will demonstrate this using MATLAB simulation. So, that means we can solve the problem of minimum off time in constant on time control problem. Now, minimum off time in constant on time control, how to summarize, like what are the algorithm? The first we need to solve the turn on problem in constant on time control, and this is particularly the case when after the switch is turned off, if we find the output voltage is below the reference voltage, then we need to turn on again after a minimum of time, and that has to be executed using a using an additional circuit. And we have discussed this, and we need to identify the falling edge of the Q, the output of the monoshot timer, and we have to delay this signal by a tau d time delay. Then we have to compare this delayed falling edge trigger signal with the comparator output. If the comparator output still remains high, then we will make an AND operation, and the output of the AND gate is applied to an input to an OR gate along with the rising edge trigger signal which was originally there, and the output of this OR gate is applied to the input of the monoshot timer. So, this acts like a trigger signal for the monoshot timer. So, we can do the similar approach for constant off time. So, I am not going to discuss. In fact, this thing we will discuss in the MATLAB simulation, but for the time being I think we can address this on time problem in constant on time control. Constant off time modulation, if we take the current based constant off time modulation, so this is similar to our peak current mode control. That means, this is my peak current reference and inductor current, and it is compared using a comparator, and output of the comparator we are putting a we are placing a positive edge detection circuit, this circuit, and then this edge is acting like an input to the monoshot timer, and here we are inverting that because we are using this as a off time, not the on time. So, we have to turn off the switch as long as this monoshot timer is high. So, this is known as constant off time modulation, and the waveforms are shown here. When the inductor current reaches this peak current, then the switch is turned off, and the switch turns off for the duration of fixed off time. This is my fixed off time, and after this off time is elapsed, then again that means the switch is on. That means this time the monoshot timer, this particular interval monoshot timer is activated, then switch again turns on and the process continues. So, we can have a similar problem, that means constant off time is constant, whereas that, and it is compared to trailing edge PWM, the time period is constant in trailing edge, here the time period is variable, but it uses a similar analogy of peak current mode control. So, both techniques directly control the peak current. Now, we can implement this constant off time using voltage based also. In this case, we need to compare the output voltage with the reference voltage the same way, and then the comparator output we are putting a like a positive edge detection circuit, and then there is a monoshot timer, and then again this is an inverted signal. So, we can face a similar problem, that means the current based constant off time control. Now, if we want to do closed loop control, then we can use a PI controller using current loop, that we will discuss in current mode control separately, but earlier we are using a fixed constant like a peak current, but now we can generate that peak current from the closed loop. Again, similar to constant on time, constant off time also have a problem of off time problem. That means, what is the logic here? Let us consider this V double dash, and suppose we want, that means when the switch is on, we want that the output voltage should be lower than the reference voltage. If output voltage is lower than the reference voltage, then this comparator output will be low. When out and after the off time, like monoshot timer completes its counting, during that time the main switch is off. After it completes counting, the main switch is turned on, and when the main switch is turned on, after some time the voltage should build up. But now, when the output voltage goes above reference voltage, then the comparator becomes high and it detects the positive edge, and then again it activates the monoshot timer. Now, what will happen if V dash double dash, that means after the switch turns off, that means your constant off time, the timer completes its timing, but after that if we find that the output voltage is above the reference voltage, that means QC will remain high. If QC remain high, there is no edge detected here. If the no edge is detected, then monoshot timer cannot be turned on again. So, as a result, the output, that means monoshot timer output is 0 and this Q will remain high. So, if the Q remain high, that means Q remains high, no rising edge is detected, then the output voltage will further increase, and it will further increase, and ultimately either voltage will exceed the limit, the specified limit, or current will exceed the specified limit. So, that means we can the similar problem will arise in constant off time, and how can we address? We can again consider a minimum on time for constant on time modulation, off time modulation. So, we can do the similar way. In fact, we can copy paste that block here and implement the logic. We can plug in with this monoshot timer. Only difference is that here is an inverted logic. So, you can do the same thing. Earlier in constant on time, it was a minimum off time that you have to introduce. In constant off time, you have to introduce a minimum on time. Okay. Now, hysteresis control, another thing. So, if you take a voltage hysteresis control, the output voltage is compared between its upper limit and the lower limit, and accordingly the output gate signal can be generated. Perhaps this can be implemented using a hysteresis comparator. A single comparator is like a Smith trigger, and we can generate the gate signal for the converter. So, you can do voltage hysteresis control. But this voltage hysteresis control, whenever we will take separately the hysteresis control, we will see for a boost converter, this logic may not work particularly during transient, because it has a non-minimum phase 0. So, you can find out that hysteresis comparator is one kind of switching control logic, and in this control logic, since we are only taking the error of the output voltage as the switching function, it is independent of the current dynamics, the switching function, it can be shown that the zero dynamics is unstable. That means the zero dynamics can be shown to be unstable. So, that is why this boost converter, the voltage hysteresis control should not be directly used unless we put a duty ratio limit or the switch limit. That means, in general the switch will remain on and inductor will saturate during a step up transient. So, current hysteresis control we can consider inductor current, and again we can keep the inductor current between the upper and lower value, the maximum and the minimum value, and we can now, if we use a fixed current reference like a upper and lower, then the hysteresis band, the inductor current ripple can be made equal to current hysteresis band. But typically that means the current ripple here is independent of input voltage and load current. So, if we use a fixed current reference, the inductor current ripple can be maintained within the reference, and the ripple current will remain same for wide variation in the input voltage, even if the load current varies. As a result, the time period will vary, because if the ripple current is kept constant, then the time period will vary for different input voltage condition. But this condition cannot be met when we design closed loop control, because the current reference, one of the current reference will come from the outer loop, the other current reference will be generated by subtracting by the hysteresis current level, that we will discuss, and the current reference will carry some ripple information of the output voltage, and which will cause some ripple effect in the reference current. As a result, the current band will not remain constant, but of course, the one band, actually if you take the minimum one, the lower value compared to the higher value, it will be less than delta IH, but the inductor current ripple will not be constant, will not be the same as the hysteresis band, that we will discuss. So, current hysteresis control we can derive, we know all this equation from the inductor current ripple. The M1 is the rising slope of the inductor current, it is the on time, this is a falling slope and the off time, and we can derive the total time, and the frequency of the under current hysteresis control can be derived by using this formula, where this is the hysteresis band. And for a buck converter, if we replace the rising slope and falling slope, then the switching frequency can be shown to be a function of the current hysteresis band, input voltage, output voltage, as well as the inductance value. So, switching frequency depends on input output voltages, hysteresis band and inductance value. So, if we operate in a wide load current range, where the current through the inductor can vary widely, and there can be some variation in the inductance value, because if we go to Bayes curve of the magnetic core of the inductor, it will not remain always in the exactly the same slope, linear slope. There can be slight variation in the slope. As a result, the inductance can vary, and if we even try to operate at a higher current, there can be saturation in the, there can be a core saturation effect, so which can drastically change the inductance value. Under such condition, this switching frequency can very much become sensitive to the nonlinear Bayes curve. That means, so you have to take care about the switching frequency if you want to regulate by using a separate control loop like a PLL, phase log loop. Under current hysteresis control for a boost converter, in the similar way, like we know the rising slope, we know the falling slope, and in our original expression we need to find out this M1 M2 by M1 plus M2, and if you substitute, then you can get the switching frequency, which is again a function of input output voltage, hysteresis current and the inductance value. So, if we want to regulate the switching frequency, the only parameter that is in our hand is the hysteresis band. If we adjust the hysteresis band, then we can keep the switching frequency constant, or we can program it according to our requirement. So, under buck converter, if you take the constant on time control, the rising slope is V in minus V0, by L, falling slope also you know, all this expression we have derived earlier. So, if we want to derive the inductor current ripple, that means if we just the switching frequency can be derived from the voltage gain, and it can be shown that under constant on time control the switching frequency is a function of voltage gain into 1 by T on. So, if the on time is kept constant, for varying input voltage switching frequency varies. If we take the ripple current expression shows that this is constant, because if we keep the on time constant. So, this expression the inductor current ripple will be maximum when this input voltage is maximum. So, this part is consistent with the PWM, where we found the maximum current ripple is coming at highest input voltage. So, under constant on time this is also consistent, but here the switching frequency will vary. In a boost converter, if we derive this on time slope, off time slope, and then if we derive the switching frequency, it is a function of input output voltage and the on time. So, switching frequency varies with the input voltage. And if we take the boost converter current ripple expression, it can be computed that rising slope into on time. Since on time is constant, then you can see the current ripple for a given on time is maximum when the input voltage is maximum. So, but in case of PWM we found the current ripple is maximum at 50% duty ratio, but here under constant on time modulation the current ripple is maximum at maximum input voltage. Output voltage ripple will be maximum at maximum load current. Again, if we derive the steady state parameter under constant off time control, since we have derived all these steady state parameter in my earlier lecture using timing parameter on time off time. So, you have to just replace those parameter and find out what are the inductor current ripple, what is the inductor current ripple expression, output voltage ripple expression, and so on. So, you can find out that T on by computing all, we are trying to find out the ripple current expression. So, for buck converter the rising slope is this, for boost converter is this, we can also show the falling slope, and the switching frequency is a function of input voltage and on time, sorry here TC is the off time, and so switching frequency varies with the input voltage. But what is interesting to see, the inductor current ripple for a buck converter, it is independent of input voltage under constant off time modulation. So, for constant off time the current ripple is insensitive to input voltage variation, whereas for a boost converter the current ripple is maximum when the input voltage is minimum. That means at the highest voltage gain you will get the highest ripple current. So, these expressions are different from pulse width as well as constant on time. So, whenever we choose any of this technique, we have to be very careful what is the worst case design, power stage design, and that is why I wanted to show that under variable frequency modulation that ripple criteria, and similarly you can find out the RMS calculation that already we have the equation. So, the power stage design need to be carefully considered when particularly you have to keep in mind which modulation technique are you going to use. So, it is not the conventional technique that we use in PWM is equally applicable for constant on time off time, it is not. So, you have to separately consider if you want to operate in constant on time, then what is the worst case, what is the worst case for constant off time, and what is the worst case of PWM. So, with this summary, variable frequency modulation we have discussed, it is alternative to PWM. Constant on time modulation, now this is this application is gaining more and more popularity. Variable frequency modulation, actually one of the problems is the switching frequency variation, and minimum on time and off time is required for whether you take constant on time or constant off time modulation, and then comparative simulation studies to be shown later. So, with this is the end of the today lecture. Thank you very much.